Sampling in OpenTelemetry is often seen as difficult, but I don't think it needs to be. There are two types of sampling in OpenTelemetry: head sampling and tail sampling. That's just a fancy way of saying it happens at the beginning of the trace or it happens at the end of the trace. Now, how and when you use those two and where they actually happen is a bit more in depth, so let's get to it. And by the way, to get the most out of this video, you're probably going to need to be familiar with the differences between spans and traces. So if that doesn't sound familiar, if you're not okay with the differences, go and check out my other video and then come on back here. Now, I'll admit for the longest time I too was confused. If I keep something, am I sampling something in? Am I sampling it out? The best way to think of this is to picture one of those fancy chocolate shops that you go into when you're on holiday. Now, in front of you are all those delicious chocolates. Which ones are you going to choose? Because you can't afford them all, you can only pick 3 or 4. So you can only sample 3 or 4. The rest of the chocolates are not sampled. You'll never know what you've missed because you didn't sample those chocolates. Now, continuing the fancy chocolate shop analogy, head sampling is making a decision as quickly as possible with really the least amount of information. So basically, you look at the chocolates on the shelf and decide based on looks alone. Tail sampling, on the other hand, would be akin to taking a bite out of each chocolate, and then deciding which ones to buy. You've got a lot more information to go on: the color, the texture, the taste, the smell, and so on, but the shop owner is probably going to charge you for each one of those chocolates that you've had a nibble out of, and so it's a much more expensive option. Plus, you're probably going to feel a little bit sick after chewing all those chocolates. So let's dig deeper into both head and tail sampling and see it in action. So we now know that head sampling happens at the earliest possible opportunity. It normally happens in the code, and it happens to the first span or the root span in a trace. So the only information you have to go on is whatever's available in that first span. Now, head sampling is great because sampling decisions can be made really, really quickly and close to the code in the microservice. Your application doesn't need to incur the cost of exporting that data somewhere, outbound, somewhere it doesn't need to. There is a downside though, and that's if you're not able to judge the trace as a whole before it's dropped. So imagine a trace crossing, multiple functions, multiple microservices, and something really important in the end-to-end view happens at some point after the trace has started, maybe, down at a database or a different microservice. You may miss that entirely because the decision has already been made not to sample that particular trace. Now, let's see what this looks like in code. Here I've got a Python application and it's configured with a sampler. Now, out of the box by default, I've got 4 options for head sampling: always on, always off, TraceIDRatioBased, and ParentBasedTraceIDRatio. You can also write your own head samplers, and I might do a video on that based on the demand. So if you want to know how to do that, let me know in the comments, and if there's enough demand for it, I'll certainly do a video on how to write your own custom head samplers. But anyway, back to the ones we get out of the box: always on and always off. Always on does exactly what you expect it to do. It samples or includes everything. Nothing is ever left out or not sampled. You get everything. Always off is the exact opposite. Every trace is not sampled, i.e. nothing is ever sent out from your service or your application. TraceIDRatio-based. So you configure this sampler with a rate between 0 and 1. So for example, like 0.1, which denotes how many traces you want to sample. In the case of 0.1, that means 10% of the traces that your app generates are going to get sent out. Now, technically how this works is that each trace ID is hashed, and then in our case, each individual trace ID has a 1 in 10 chance of being sampled. Said another way, every trace individually has a 90% chance of being dropped. You configure this in exactly the same way as the TraceIDRatioBased by providing a rate, but the difference is if the current span has a parent span, this sampler respects the decision of the parent. In other words, if the decision of the parent span was to sample, this span will be sampled, regardless of the rate. If the parent span decision was do not sample, it'll also drop this span. If there is no parent span, then this one behaves exactly like TraceIDRatioBased, and we calculate the rate. Now there's a subtle but important point on the above rate calculation. So we're using the example of 0.1 or 10%. Imagine I have an app that generates 10 traces. You'd expect logically to get one trace every single time. 10% of 10 is 1, right? Well, not always, because sometimes you might get 0, you might get 2 or 3, but most of the time you'll get 1. And that's because the 10% calculation, that decision, happens on each trace individually. And so each trace has a 1 in 10 chance of being sampled. So on average, you're going to get one trace, but that explains, if you're looking in the logs, why you sometimes might get more and sometimes might get less. So that's head sampling. Quick, it's efficient, but it is done by design without having the full picture of the trace. Now let's look at tail sampling. It's the exact opposite of head sampling. Tail sampling waits until the very last moment, until the trace is complete, until you have all of the information possible, so that when you make that decision whether to sample or not, you have as much context as possible and the most full picture before making that sample or do not sample, the call to keep or throw away. Tail sampling allows you to make that decision based on information from anywhere within the trace, so any span within the trace. Think about a distributed system of microservices. Tail sampling allows you to gather and then keep or discard an entire trace based on a value from a microservice, which might have been 8 or 9 or 10 hops after the original entry point the user clicked the button. Now, because tail sampling happens at a different stage in the life cycle, it also happens in another component, usually an OpenTelemetry collector, or in the back end of the vendor's observability platform if you're paying for a vendor. But this also implies that to use tail sampling, your architecture is probably going to change. Think about it. If tail sampling is looking at the entire trace, all the spans that make up that trace to make the decision need to be in one place. So the component making the decision has to have all of the spans that make up a particular trace. In practice, this usually means arranging for all of the spans for a particular trace to flow through a single collector instance. Now, while tail sampling is more powerful, definitely, it is more complex. Your architecture, as I've said, is probably going to change, your collector architecture. It does require more effort and more maintenance. It isn't just as simple as, keep 10 or 15% of my traces. As your systems and your business requirements change, you'll need to update your sampling rules and configurations to match your new architecture. And the components doing the tail sampling become stateful. This is a big one because, as I've said, they need to hold all of the spans until the trace is done before they can make a decision. By default, collectors are stateless, so bear that in mind. Now, with all of that said, you might be tempted to say no, absolutely not to tail sampling. But in reality, I've worked with customers who do both head and tail sampling, because it really depends on your use case, your appetite for complexity, maintenance, and your need for cost saving. Let's have a look at how we actually configure the collector for tail sampling. So throughout these examples, our example Python will emit 10 traces per run, and all of these spans are being sent to a single collector. So the first question you probably got is, how does the collector know when the trace is actually done? And think about it. If you have a highly distributed microservices architecture and the spans are arriving at different times from different places, how does that collector actually even know that the trace is done? There's no indication of how long the trace is, before it happens. And the answer is it doesn't really. The best that we can do is say to the collector, well, when you see a span come in, with a trace ID that you've never seen before, start a timer and wait for a certain amount of time that you decide. And after that, just assume that you've received all the spans for that trace, and then go ahead and make a keep or drop decision. We can configure that wait period with the decision wait parameter. Here, for example, I'm waiting for 5 seconds before making that sample or do not sample call. And here is your first challenge with configuring tail sampling. Depending on the system or systems you're observing, you may have some traces that you know take 5 minutes to complete, but other traces that only take a few seconds, in which case you probably need to find a way to process these types of traces differently, potentially routing them to entirely separate collectors for dedicated processing. The next question you probably got is, well, how many spans, if we're storing all of this to make a decision, how many spans does the collector even store? And remember that tail sampling has to store all of those spans for a particular trace before making a decision. But obviously it can't store an unlimited number of traces and spans. So how do we tell it the limit of what it can store? The num traces parameter is exactly what you need. Now, by default, this is 50,000 in a ring buffer, meaning it will store 50,000 traces in memory on the collector. Here I have set it to a much more modest 10 traces. So if new traces come in over that limit, the old traces will be removed from the buffer. It's just a ring buffer that goes round and round and round forever. There are a few other parameters that I'm not going to get into, dealing with memory allocation and pre-allocating the size for the sample, or do not sample, the so-called decision cache. But these are optional parameters, so check out the documentation if, in the future, as you use the tail sampling processor, if you find that you need to tweak them. The defaults should be okay to get you started. Okay, you've configured the basics of the tail sampling processor, and now we get to the really good stuff, the rules that you write on whether to sample, keep, or do not sample, throw away your traces. Now, these rules are called policies, and as you'll see, it is an array, so you can define multiple policies. But before we get into the individual policies, I have a top tip. Trust me, comment your policies, because they may look obvious to you today, but policies do get very, very complicated and interlinked, and future you is going to be really grateful if there are human readable comments explaining, each policy and your decisions as to why they are there. First up is the most basic policy. Keep absolutely everything. As you can see, we have a single policy and the type is always sample. That means keep everything. Next up, there are two ways to drop everything. The first way is to create a drop rule that matches every single trace, i.e. drop everything. And the second way is just to have an empty policy array which matches nothing, so everything is dropped. Just like we did with head sampling, you can also decide to keep a percentage of traces using tail sampling. Here we're deciding to keep or sample 10% of the traces. The same sampling logic applies here as it did to head sampling. Each trace ID is evaluated individually, so you'll get that behavior again where sometimes you get none, sometimes you get more, but usually you get 10%. This policy searches every span within a trace, and wherever an attribute key of foo and with a value of bar is found, the entire trace is kept. So think about a real system. You might have crucial user or transaction information that's added to a span in the trace that's, on the 11th hop in the chain all the way down at the mainframe, but you want to keep that entire end-to-end trace from when the user clicked the button on the website. And this is a way to do that. And yes, the values field is an array, so you can list multiple potential values, and this also supports regex, which I'm not actually showing here. This policy samples or keeps the entire end-to-end trace when any of the samples in that trace have errored. So again, imagine a distributed system and you want to see traces whenever an error has occurred in any component, in other words, in any span across the entire request, not only the errors that are in the initial span. This rule only samples traces or keeps traces which are sending fewer than 10 spans per second. This can help protect against over-instrumented services or heavy traces. This rule samples traces that have fewer than 20 spans. The flip side to over-instrumentation is under-instrumentation, and this is obviously an equal problem because if something is under-instrumented, you don't really have enough information in the trace. Rather than having too much, you don't have enough to make the end-to-end picture actually useful. We've all seen single-span traces that hit the front end and stop. I mean, health check pings are a prime example of this. Having a single-span trace isn't very useful at all. So perhaps you just want to sample or save traces that have more than a certain number of spans, i.e. at least 5, and then you know there's at least some information there. It's good enough to start your investigation. Of course, you can combine both of these conditions to sample traces that are just the right length for you, but obviously you need to decide what that right length is. Here's how to configure a drop traces rule to keep all the traces except traces that contain a span with an attribute of foo bar. The way to read this is drop all traces where one of the spans in that trace contains an attribute of foo and a value of bar, and keep the rest. It is also possible to define sampling rules using the OpenTelemetry transformation language. You might know it as OTTL. And this flexibility opens up almost unlimited possibilities to really target precisely what you need to target in those spans. So here is the equivalent keep traces containing foo bar that we saw previously, but written in OTTL. It is possible to generate policies with multiple conditions. For example, this policy samples or keeps traces where all of the following are true. 1, a span in this trace contains an attribute of foo bar. 2, a span in this trace contains an attribute of user tier is gold, but it doesn't need to be the same span. And 3, a span in this trace contains a key of order total with a value that's greater than 500. But remember, they don't need to all be on the same span as long as they're in one span within the particular trace. The tail sampling processor does also offer so-called composite policies, but I'll be honest, I can't figure out from the documentation what they are, and I've never actually seen them used in practice. But if you know what they are and can explain it, please do drop me a note in the comments. I'd love to know and figure them out myself. So there you are. That's a deep dive into head and tail sampling with the OpenTelemetry collector. I hope you found this useful and you now find sampling easy-ish. It's never going to be easy, but hopefully this makes it a little bit easier. If you have any questions, ideas for future videos, please do leave a comment, click like, subscribe, all that kind of good stuff. Thank you so much for watching, and I'll see you again very, very soon. Bye.